Hello guys, welcome back. So in this lecture, let's quickly discuss about time complexity and space complexity of quicksort, right? So in the previous lecture, we have seen like how it works in the call stack in terms of call stack in browser. So let's quickly finish this. This one will be the quick one, right? So as you can see here in the screen, the time complexity of quicksort is similar to merge sort, right? In terms of best and average case. But in terms of worst case, it is O of n square. Okay. And space complexity is O of log n. Right. So let's quickly see the best case and average case for quicksort, like how we got log of n. Right. So let's say you have an array. Right. So let's pick this one. Why I have to pick write a random array every time, right? Okay. So let's pick this one. Okay, so here if you see, let's say we pick a pivot point as this, and then what we have to do, we have to do decompositions, right? So all the elements which are smaller than, or we can take this one, all the elements which are smaller than this one, we have to decompose them like this, and again from here we have to pick one pivot point and then we have to decompose it. Okay, so we took the pivot point like this and then we have to decompose it like this. See, 2, 1. Okay, and then again here we have to pick a pivot point. Let's say pivot point is 2, and then we have to decompose the array like this. Okay, and same thing which we have to do here. Okay, so if you see, if the array is of length n, then there will be just few decompositions, right? Okay, so we are picking the elements which are smaller, we are moving them into one array, and then we are decomposing it, right? So from here only we got the log n, right? And then if we are decomposing it, if you remember, after decomposing, we are comparing the elements, right, to see which one is smaller, which one is larger. Then only we are swapping the elements, something like that we are doing, right? So from there only we are getting comparisons, right? So from there we are getting O of n time complexity. Okay, so the decompositions of this one is going to give us log n. Okay, so log n is coming from here. We have an array, we are picking a pivot point, we are decomposing it, and then from this array we are picking a pivot point, we are decomposing it. Okay, let me zoom it a little bit. Right, so log n is coming from here. Doesn't matter like how big our array is, every time it will end up like within 5, 6, 7 or somewhere like in single digit steps, right? Not every time, but most of the times, right? So from here we will get log n, and then when we start comparing them back and then we return those things back. Okay, so let's say we have these two elements, we checked which one is smaller, which one is larger, we have swapped them, and then we moved on to the parent array. Here we did the same thing, we checked which element is smaller, which element is larger, we arranged them accordingly, and then we moved into the parent array. So this way, in from comparisons we are going to get O of n. Okay, so from decomposition we are going to get O of big O of log n, or let me write big O only, right? And from comparisons we are getting big O of n, because there will be n number of comparisons, right? The number of elements which we have, the same number of comparisons we are going to have, right? Because every single element we are going to compare with all the elements, if you remember, right? Then only we'll be sure like which element is smaller than the pivot point which we have picked, and which element is larger than the pivot point which we have picked. Okay. So the comparisons will be O of n. It will be same as the input size, right? So this will give us big O of n log n. So this is for the best and the average case scenario. So best case, I mean like if the array is, we can say almost sorted, right? But there will be and average case also, like if the array is almost sorted or like totally unsorted, we can say, right? Now if we talk about the worst case scenario, see here in the quicksort, the worst case scenario will be a little different, right? So if you pass a random data, if you pass an array like this, okay, it's totally unsorted, it's kind of unsorted only, right? So for this, it is working fine. It is decomposing it into some steps. But the problem is, if you pass a totally sorted array, let's say 1, 2, 3, 4, 5, 6, okay, and you are picking the pivot point as number 1. So what will happen on every decomposition, you are going to get an array like this. 1 and then this one. And then in the next decomposition, you are going to get this. And next decomposition, you are going to get this. Why? Because you have picked this as a pivot point. There is no number which is smaller than 1. So all the elements will go on the right side. Okay. Same will happen with this. Same will happen with this. Same will happen with this. And same will happen with this. Right. If you see, now we have O of n comparisons. O of n decompositions. The number of elements which we have here, the same number of decompositions we have here. Since we have picked the first number, it is a sorted array. We know it's a sorted array, but our program or algorithm doesn't know it's a sorted array, right? So what it will do, it will try to decompose all the elements. It will try to move all the elements which are smaller than the pivot point in the left side and larger than the pivot point on the right side. In this case, we don't have any number which is smaller than our pivot point. So all the numbers will be moved to the left side, and same will happen for every element. If you see, whichever element we are picking next is the greater number. It doesn't have the smaller number side. Okay. So yeah, this way from decompositions we are going to get, or let me just quickly get it from here. Okay. So from decompositions we are going to get O of n, right? And then since there are O of n decompositions, after decomposing we are going to compare them back, right? So the number of elements which we have, the same number of comparisons we are going to do, right? To see the number which we have picked is smaller than which number or larger than which number. So we'll adjust those numbers accordingly. Okay. So from here in comparisons also we are going to get O of n. Okay. So it will end up giving us O of n square. Right. So from here we are getting O of n square in the worst case scenario. So we can't say like we have a proper solution for this, but what you can do, instead of picking like the starting number or the end number as the pivot point, you can pick any random number from the between. Okay. And that is also not we can say a legit solution every time, because let's say you have an unsorted data, but accidentally you have randomly picked a pivot point, but that is the smallest element in the array. Okay. Then it will still end up decomposing it like this, right? So we can do our best to pick the random number as a pivot point from the array, but end of the day, like in the worst case scenario, we cannot escape the worst case scenario as O of n square. Okay, that is the truth for the quicksort, right? So from here, we are going to get O of n square for the worst case. And okay, let me just quickly O of n log n and O of n log n basically for average case and the best case, right? So let me quickly cut it from here. Let me paste it here as example. Okay. So in case if you guys want, you guys can take a screenshot of it. Right. Okay. So you can take a screenshot of this one and then you can take a screenshot of this one as well. Right. So this is how we are going to get, time complexity of best and average O of n log n, and space complexity. If you talk about, then space complexity, if you go here quickly, right, if you go here in the pivot function, as you can see, the number of times we are decomposing, we are occupying some space, right? So from there we are getting O of log n, right? So that means like we have some not constant, like sort of constant space complexity here, right? So yeah, this is it about time complexity and space complexity of quicksort. Now let's jump into the next interesting sorting algorithm, which is radix sort in the next lecture. Okay, so this is it for today. See you in the next one.